Sometimes I explain this to people and they give me blank stares.
Okay, I have my desire.
Okay. Beauty is in the eye of the beholder, and the beholder has a stung eye.
Wow.
Glad I prepared that.
So hi everybody, my name is Kyle Geske, and I'm here to talk about Alan Turing's 1936 paper on computable numbers with an application to the Entscheidungs problem. And this is the paper in which Turing invents a theoretical model for computation before computers existed. So we're around the time frame when people are starting to think about computation, are starting to think about the ideas of sort of mechanical mathematics. And Turing creates this model for computation, but he does so really without, the purpose is not to create a computer. Alina. The purpose is to attack this thing called the Entscheidungs problem. So the computers are sort of a side effect of that process, which is sort of the interesting thing is most people remember Turing and this paper for this theoretical model of the Turing machine, but that wasn't really his intention. And so before I can talk about the paper, I'm going to sort of break down the title a little bit. The two major components of the title are the idea of computable numbers and something called the Entscheidungs problem. So I'll start with computable numbers. And so these first two things are quotes, and they're quotes basically just from Turing, from the paper itself, describing what a computable number is. And he says that computable numbers are a subset of the real numbers whose decimal expression, or whose expression as a decimal, are calculable by finite means. This doesn't mean the number itself is going to be finite. Most of the numbers that Turing's machines calculate are infinite, but they can be expressed as a series of operations that can be expressed in finite steps. And a number is going to be said to be computable if its decimal can be written down by a machine. And he also restricts the computable numbers to be binary numbers. He actually uses fractional binary numbers in the range of 0 to 1. And so an example of a fractional binary number, if we looked at the decimal number 1/3, if we wrote this out in in decimal, we would say, 1/3 is 0.3333 forever. And if we were to write it out in base 2, we would say it was 0.01010101, and the 01 is going to repeat forever. So those are the kind of numbers that Turing's machines are going to produce. And he assumes this part. He assumes the 0 point. So if he was to create a machine to print out the binary equivalent of 1/3, it would just start directly after the decimal place, and the machine would print out 01010101. And I'll get to what I mean by printing in a moment. So there's actually a printing device on these theoretical machines. So that's the concept of a computable number. Then we also have this idea of an Entscheidungs problem, and it's a German word. Entscheidungs means decision or decidability, and this idea of there being a problem around decidability in mathematics and formal systems came from David Hilbert, a German mathematician who was part of the formalist school of mathematics. And so in the formalist school, they believed that mathematics was just pure symbol manipulation, that there was no meaning associated with any of the math except the meaning that we as humans attach to it. And that was the power of formalism. You could create this wonderful formal system, and you could attach it to observations about the real world, and you could get something like Newtonian physics from that. And so formalism was a very optimistic look at mathematics. Hilbert believed that there was basically nothing that humans couldn't learn using formalism, that everything was discoverable, and eventually we would know everything, and we would know it because of the power of math. And so Hilbert believed that an ideal formalist system or an ideal mathematical system was three things: consistent, complete, and decidable. Consistent in that it contained no contradictory, well-formed formula. Complete in that all true formula could be derived from the axioms of the system, and they could be derived, again, purely mechanically through symbol manipulation. Gödel quickly disproved both of those things, and that's a completely other talk that may happen in May. So the formalist camp was being attacked on these three ideas. The first two fell to Gödel. Turing is going to attack this third one, this idea of decidability, and that's the Entscheidungs problem. So what decidability means is that Hilbert considered or assumed that there could be a finite decision procedure to determine the provability of any given well-formed formula. And I'm going to give you an example of that. And first I'm going to give you the example in terms of algebra. Hilbert originally looked at it in this way, and then he expanded it out to all formula systems and further to like first order predicate logic. But I think it'll make a bit more sense in terms of algebra. And so if you think about an algebraic problem that you perhaps have two cubes. So I'll draw two cubes here. This cube has a length, height, and width of x. This cube has a length, width, height of y. And if I was to say, well, when you add those two together, you get 10. And if you were to add the volumes of those two cubes together, so x cubed plus y cubed, you would get 370. Now, decidability is not the idea that Hilbert didn't want like a mechanical process for figuring out the answer. Humans can do that, right? We could sit and like mess around with that formula, plug and chug it, and if it was provable, we could get to an answer. This one has an answer. I think it's like, you can cheat here and just look. X is 7 and y is 3, and so you could verify that. What decidability meant was that maybe you didn't know up front that there was an answer to that problem. And there's this, when Hilbert first proposed this, what he was looking for is he wanted to know if you could formulate formulas like that and know just by looking at them if there was a solution in whole numbers. So he wanted a process, again, a purely mechanical process that could look at these formulas and say either thumbs up, this is provable, you can find a solution in terms of whole numbers, or thumbs down, it's not. The reason he wanted to do this is he wanted the ability to sort formulas. You could look at all the possible formulas. You could, if you had a formula system, you could even generate those formulas, and you could put them into two buckets, those that are provable and those that aren't. And that way you wouldn't have to spend a whole lot of time sort of wasting your time on trying to prove things that are unprovable. If I tell you straight up from the beginning that there is an answer to this question, you just know you have to work long enough, and eventually you're going to get it. If you don't know that there's an answer, you never know when to give up, right? If you worked 5 more minutes, you might actually find that answer. So that's what Hilbert was looking for. So originally he poses it in terms of arithmetic, and then he later expands it out to sort of all formal systems, and sort of specifically the one that Turing takes to task is first order predicate logic. So those are the two initial concepts, these computable numbers, the decision problem. The reason that Turing thought of creating an abstract machine to attack this problem is that one of Hilberts' assistants, when he wrote about the decision problem, he said this. He said, "Is it of fundamental importance for the character of this problem that only mechanical calculations according to given instructions, without any thought activity in the stricter sense, are omitted as tools for the proof? One could, if one wanted to, speak of mechanical or machine-like thought," and then he added, "perhaps one could later let the procedure be carried out by a machine." And so Turing took this to be a challenge. He thought, well, maybe I will come up with this machine and see if it's even possible. So what did he start with? He started with human thought. And so he modeled what we now call Turing machines. He just called them sort of computational machines, or often just the machine. He modeled it on how we solve problems when we're doing mathematics. And so what he said that we do is that we work with a finite number of symbols. So we're manipulating a finite number of symbols to get to some result. In our own minds, we have discrete states that we're switching between. So if I'm doing a little bit of math, I'm like adding 378 with 13. I might have various discrete states of mind. I might say, okay, first I'm doing addition in the first column, and I would do that, and I would say, okay, that's 11. Now I switch to the next state of mind, which is to carry the one state, and I would carry it over here, and I would go to the addition in the second column state. And so I'm holding these discrete states of mind that allow me to carry out this problem. And finally, I'm working here on a board, but Turing had the person working on paper to do two things. One, to use the paper as sort of scratch base for intermediary results, and also to record the final results. So Turing wants to build, he doesn't actually want to physically build it. This machine he comes up with is hugely inefficient, but he wants to sort of come up with this idea of an abstract machine that can do these three things: manipulate a finite set of symbols, have discrete states of mind, and perform calculations and record them on some kind of paper. So for the states of mind, he uses a tool that already existed in mathematics, and that is the tool of state machines. So if you don't know what a state machine is, it's an abstract mathematical machine or concept that can be in one of any number of finite states. It's in only one at a time, and that's called the current state. And it can transition, usually by way of input, from one state to another. And so this diagram here is sort of a state machine for the game Pac-Man, right? So you might start off wandering the maze. If you spot Pac-Man up on that top, that's going to be an input to the wander the maze state, which will allow you to transition to the chase Pac-Man state. If Pac-Man eats a power pellet, you're going to start transitioning down to fleeing Pac-Man, and so you're moving from discrete state to discrete state. A more simple example of a state machine is a turnstile. So you can imagine these likely existed in Turing's time. I'm not 100% sure, but it's like a one-way gate. You go to like a subway station, the gate's locked, you pay some money, the gate unlocks, you're allowed to go through the gate. So we have some states that we can work with here. We have one state, which is our locked state. We have one state, which is the unlocked state. And then we have some inputs that will allow us to transition between those states. So if I input a coin when I'm in the locked state, that coin is going to allow me to transition from locked to unlocked. Once I'm in unlocked, I can continue to feed the machine coins, and it's not going to change the state at all. So I'm going to have this kind of loop back state. So inputs of coins when I'm in the unlocked state are not going to change the state. If I push on the lock, it's going to let me through, and then it's going to transition from unlocked back to locked. And when it is locked, no matter how hard I push on it, it's going to remain locked. So that's a very simple state machine. So Turing's going to take this idea. I've written it out in a slightly different way in sort of a table here. So those are our two current states, the inputs they might receive, the next state that would be the transition, and what kind of sort of output or effect that would have. Turing's going to take this idea and he's going to add something to it. Right now, as it stands, this state machine really is read-only. It doesn't have any way of recording results or affecting the world other than its transition between states. Like the machine itself can change from locked to unlocked, but it can't remember its previous state. It can't remember how often it was locked or go back and think about or introspect on its lockedness or unlockedness in the past. And so what Turing wants to do is he's going to add a tape. And so if you think back to his three things he's trying to model, we've got the discrete states of mind now by way of the state machine, and he's going to add the piece of paper. So he's going to say this fictional machine of his, or this abstract machine, is going to have a tape, a paper tape, or it can be any really kind of tape he didn't specify, and it's going to be able to read and write to this tape. At any given time, there will only be one symbol of the tape being read or written to. The position of the tape can also be erased, and the tape is going to be of infinite length. And often it's just of infinite length in one direction. So a lot of Turing's machines just start writing numbers and they write them out on the tape in one direction forever. And now what we have, which is really interesting, now we have the ability to add memory to this state machine. And we can use the symbols that are being read back from the tape as further input to a state machine that we devise. So state machine plus tape is probably the simplest computer you can make. Turing's machines are not efficient. You probably would not want to build one. They can do anything that our modern computers can do, but they would probably do it very slowly, and programming them would be very, very difficult. What happens, the way the sort of the process goes, is that the machine's current state, when combined with the currently scanned symbol, Turing calls this the configuration, and any given configuration can lead to a change in the state, writing of a symbol to a blank square, erasing a symbol from a square, or moving the tape a single space either to the right or to the left. And so I'm going to give you an example of a very simple Turing machine, one that's going to print out that binary number, which was the equivalent of 1/3. It's not going to do any calculation, so this machine's not going to calculate 1/3 by dividing 1 by 3. It's simply just going to print out a series of zeros and ones for an infinite amount of time. So it'll print out 0, 1, 0, 1, 0, 1 forever on a tape. And it's going to do so by way of a state machine. It's going to have only two states. There's going to be state A and state B. And if you look here, those are my two states on the left. This machine is so simple, it doesn't actually need the symbol being read. The symbol being read is always going to be blank. It's going to be the next blank square that you're about to write to. But the way we're going to read this is that when I'm in state A, and there is a blank symbol under the read head, or the read-write head of the machine, I'm going to print a 0 and move to the right, and then transition into state B. So I'll write that out by showing that transition. The first thing I'm going to show here, I'm going to use a B with a slash through it, that's going to represent blank. And so this is the input. When I'm in state A and the input is a blank symbol, I'm going to print a 0 and move to the right. When I'm in state B and the input is a blank, I'm going to print a 1 and move to the right. And now we have a theoretical model for a machine that can print an infinite series of zeros and ones. Not very interesting yet, but it can do its thing, right? So if I have my tape, I can actually act out the machine. I don't need to interject any thought into the process. I can just carry this out in a very sort of machine-like way, right? So I'm going to start in state A. Sometimes Turing has like a begin state that always just transitions to kick off the process. And so maybe I'll use something like this to demonstrate what state I'm in. So if I'm initially in state A, I see a blank square. My read-write head is currently here. And so I'll print a 0, I'll move to the right, and now I'm in state B. When I'm in state B and I read a blank square, I'll print a 1, and I'll move to the right. I'm now back in state A. When I'm in state A and I see a blank square, I print a 0, I move to the right, and I transition. And I'm going to do that back and forth, moving along transitioning through the symbols. And I'm gonna, as long as you keep running that machine, it will print out its zeros and ones on its infinite tape. So in the paper, that's the very first machine that Turing shows us. It doesn't even yet need the read capabilities of the tape. It's only using the write capabilities of the tape. I'm gonna show another machine now. This one, Turing does not include in his paper. The next machine he gets to is actually pretty advanced, so I wanted an intermediary one to step through, and I wanted one that would do something a little bit interesting. So this one's going to be a machine that will count in binary, and it breaks a few of the conventions that Turing imposes on his Turing machines. So he has some conventions where when he presents this machine, he actually has these figures print on every other square, because he's trying to set himself up for future more complicated machines where the blank squares can be used as scratch space. And he also has a convention where he will never erase a figure once it's been written. So if it's not in one of the scratch spaces, once it's been written, it's there permanently. With this machine here, that's not going to be the case. We're going to just allow us to break convention a little bit. So I'll leave my Turing tape like that. So as a human, if I'm going to count in binary, I'm going to start at 0. I'm going to go to the next number. I'm now at a 0. I'm now at a symbol, so I got to go back to 0, and I got to carry that 1 to bring me to the number 2. I count up to 3. 0, 0. Carry the 1 all the way over. Get to me to 4. I'm going to run this machine until we get to 4, and we'll just sort of see that it's actually going to do the same thing that I'm going to do. If I spent some time thinking about my way of counting in binary, it's probably algorithmic as well. I'm following just a certain set of steps. This machine is going to break it down into 3 different states. There's going to be like a beginning state, which we're just going to call B, an incrementing state called I, and a rewinding state that we're going to call R. And it's going to transition like this. I'm just going to cheat a little bit, and I'll take what's in this table and draw it out as a state machine. So when we're in the begin state and we see a blank, so here's our blank, we're going to print out a 0. When we're in the increment state, there's 2 ways for us to get over to rewind. So we can get to the rewind state if we read a blank, or if we read a 0. In both cases, we print out a 1 and then move to the rewind state. So if it's a blank and a 0. If we read a blank, if we read a 0, print a 1, and we print a 1. When we're in the increment state and we see a 1, this is in with the read-write head again, then we're going to print a 0 and move to the left and stay in the increment state. So when we see a 1, we're going to print a 0 and move left. And the way that rewind is going to work is that when we read a blank, we're going to move to the left and then transition to increment. So that takes us here. So we see a blank. We are going to move left. And if we see any non-blank character, a 0 or a 1, we're simply going to move to the right and stay in the same place. So we're going to see a 0 or a 1, we're going to move to the right. So that is now a fairly complicated Turing machine. I'm going to start with my read-write head right here. I'm in state B to begin with. I see a blank square under the read-write head, so I print a 0. Print a 0. That gives me the transition to this state right here. I now see a 0, and so my input is 0. That's going to cause me to print a 1. So I'll print out a 1, and that'll transition to this rewind state. When I'm in the rewind state and I see either a 0 or a 1, I start to rewind. I go back in this direction, so I move back over here. I'm still in the read-write state, but now I see a blank. So I'm going to move to the left, transition back over here. I've now counted to 1. To get to the next number, I'm in this state right here. I see a 1. I'm going to print out a 0. And I'm going to move to the left. And I'm going to remain in this space. I'm now in the increment space. I'm sitting over here. I see a blank space. I'm printing out a 1. I've now counted to 2. I'm going to transition over here. I now need to rewind back to the beginning. So as long as I continue to see a 0 or 1, I will move to the right. I no longer see a 0 or 1. I see a blank. I move over here, and I adjust myself back to there. I can now see a 0, which I will overwrite with a 1. I've now counted to 3. That will allow me to go over here, and the process continues. And if I let that machine, me being the machine, run forever, I would just continue counting in binary. And because I have an infinite tape, my binary number would become larger and larger and larger, and I don't have to think about the process. There's nothing human intelligent going into that. I'm simply following out the rules of the machine and reading the symbols under the pointer. So those are 2 examples of Turing machines. Turing now sets up 2 different kinds of machines. He talks about machines that are circular or machines that are circle-free. And a circular machine is going to be a machine that gets stuck in an infinite loop. So for Turing, his machines are going to be considered functioning if they infinitely produce numbers, if they continually write 0s or 1s on the tape to the right, calculating a number to an infinite precision. So that first example of the 0-1 machine, we're letting it write, it's printing out 0s and 1s forever. It is in effect stuck in an infinite loop, but it's doing productive work. So when the machine's doing productive work, Turing says that it's like circle-free. That's a happy machine. And when you have a circular machine, that's sad. That means the machine has stopped printing figures. It's no longer printing out 0s and 1s, and it's caught in some kind of infinite loop. It's in a state where it's just sitting there, looping in a circle, and it can't return to somewhere where it needs to do the actual work. This is going to become important when Turing wants to show the limitations of the machines that he has come up with. So I'll leave those pictures there so that when I start talking about circle-free versus circular, you can know if that's a good thing or a bad thing. So what Turing does next is pretty interesting. He says, look at these tables we've been building to talk about our machines. Each one of these tables has rows, and each row has a current state, a current symbol, some behavior, a printing, a moving, and then a next state. What Turing's going to say is that we can actually take each one of these rows and encode them as a quintuple of symbols. And he's going to say we have the symbol Q, which is going to be the current state, S, which is the symbol currently under the read-write head, Q primed is the state we're going to transition to, S primed is the symbol that's going to be written in the place of the current symbol, and D is the direction to move, left or right. And so our earlier machine, this one with the 2 states that could just print out 0s and 1s, we could write it out as a computer program. So Turing says, okay, you can just describe these things in quintuples, you can write them down. This machine starts in state A. When it reads in a blank, it's going to transition to state B, draw a 0, and then move to the right, and then the other configuration is described there. So he's come up with a way of encoding Turing machines, and this is going to lead to some very interesting stuff. One thing that it leads to is that now that we can write out a machine as an encoded set of symbols, we could replace each one of those symbols with a number. And what we've done now is we have the ability to describe a Turing machine as a number, which if you are a computer programmer in today's world, all of our executable programs are just numbers. You compile a program, you write it to disk, it's one large binary number. And so Turing discovered this, or realized this very early on, that every program can actually just be represented by a number. What that gives us is the fact that you can create a really special and complicated Turing machine. And what this Turing machine can take as input is one of those numbers. It can take as input the description of another machine. And then Turing spends a long time actually building in math that universal Turing machine. A Turing machine that can read in a description of a symbol like this. And what it's going to do is it's going to be able to simulate any Turing machine that you give it a description for. So that means we can build a Turing machine U that can take as its input on its tape the description of a machine M, and then U is going to output successive snapshots of the current state of the simulated machine and the current tape of the simulated machine. And so it's going to be able to simulate any given Turing machine. This is pretty crazy. When I first read Turing's paper, I was pretty satisfied with just his plain old Turing machines. I thought, okay, these things are single purpose, but they do calculations, they actually perform a task, but it's nothing like modern computers, because modern computers are general, they're not single purpose. We can program them to do anything. And then I turned the page, and Turing says, but we can actually do anything. And he goes and shows that you can create programmable computers. So computers don't even exist at this point, and Turing's already made a programmable computer, one that can simulate any given computer. And this is where we get that concept of calling things Turing complete. Turing machines are so incredibly simple but they have this power of being able to simulate any other machine. So even if you try to create a really, really powerful or complex machine, you're no more powerful than a Turing machine, because Turing's machine can simulate your machine. So any kind of machine that is describable can be simulated with a Turing machine, meaning that there is nothing more powerful than a Turing machine. And so when we talk about programming languages being Turing complete, once you reach a certain level of completeness in the language, you have no more power in your language than any other Turing complete language, because you can simulate any other language if you wish to. That brings us to the whole point of the paper. So the point of the paper wasn't to create these Turing machines. The point of the paper was to show that the decision problem was not solvable, to put the final nail in the coffin for formalism. And so Turing does this by showing three things. He first comes up with an uncomputable number, because he wants to show that there are certain things that these machines cannot do. So he's going to come up with a description of a number that is completely describable but not computable. Then he comes up with what we call these days the halting problem, and then he spins that around to attack the Entscheidungs problem. So I'll start with the uncomputable number. This is where things get a little bit heavy, so bear with me. I hope I won't make any logical errors. Make sure I have my notes at my disposal. Yes. And so, if every Turing machine description is just a number, Turing tells us that that means that these machines are enumerable, meaning that we could have a set of all machines, and we could say in that set there is some machine which is machine 1, and another machine which is machine 2, and another machine which is machine 3, etc., etc. That set will be infinite, but there should be an enumerable set of describable machines. And for each one of these machines, so these are our machines, each one of these machines will compute a number. So So there'll be an associated computable number with each one of these machines. So we could say like machine 1, let's say it happens to be that first machine that we looked at, a machine that just goes 0, 1, 0, 1, 0, 1 forever. Machine 2, Turing shows us a machine that goes 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, etc. And then maybe machine 3 prints out a 1 followed by an infinite number of zeros. Turing now asks us to think about another machine and also a number. So I'll start with the number. This is going to be the uncomputable number. He's going to give us a description for it, but he's going to show us that there's no way you could possibly compute this thing. And the way we're going to build this number, and it should be a computable number, so it should be somewhere in this list. It's going to be some machine, k, it's going to compute a number, beta, and the definition for beta is that you're going to take each machine in your set, and according to its numeric value, the position in the set, you're going to take the digit at that place and record its binary inverse, or its logical opposite. So for machine 1, we'll look at position 1, and we'll write down the opposite, which is a 1. For machine 2, we'll look at position 2, and we'll write down its opposite, which is a 0. For machine 3, we'll look at position 3, and we'll write down its opposite. Sounds pretty describable. You've got this enumerable set, you've got a machine that can calculate things out forever. Let's do this thing. The thing is that this machine that's calculating this number should be in this list somewhere. So somewhere in this list should be mk. And it'll start, in our case, with 101. And then at some place, there will be the kth position of this sequence. That'll be right here, the kth position. If that kth position is a 0, then the kth position down here has to be a 1. But these are supposed to be the same number. And so that's impossible, right? And even if this was a 1, when we go and read it, we're supposed to say, well, we read the kth symbol, just like when we read the first symbol, we recorded its opposite. When we read the kth symbol, we record its opposite. Oh no, it's actually a 0. But again, these two things are supposed to be the same number. So there's no way to compute beta. It's like logically impossible. So that's Turing saying, okay, my machines are awesome, but they have some limitations. There are certain things they cannot compute, and he uses this diagonalization argument to show that there is a particular number, in this case beta, that is not computable. That's pretty neat. He's building his way now towards attacking the decision problem. This is step 1. Step 2 is what we now call the halting problem. And the halting problem, I can best describe it as giving you an example of sort of what happened when I was going through computer engineering. So going through computer engineering, learning how to program, one night having some beers with my buddy, and my buddy Bruce says to me, Kyle, every computer program is just a number. I said, yeah, that makes sense, you're right. Like, it's a binary number that gets written down to a hard drive, that's cool. And he's like, well, we can generate random numbers. I said, yeah, that's also true. He's like, well, that's the infinite number of monkeys in a room on typewriters, man. We can now create any possible program. Let's just generate programs and run them. It could generate anything. You could generate a program that solves cancer. It's like, wow, that's crazy. We can do this thing. And then we start thinking, well, no, there's some limitations here. Like, most of these programs are straight up just going to crash, right? They're just not going to be well formed. And the ones that do run, well, who knows how long? They might just sit there calculating away. Maybe they're coming up with the solution to all of the world's problems, but how do we know how long to wait? How do we know that they haven't spun themselves into an infinite loop? And so then we thought to ourselves, well, we just need to write a program that'll inspect these things, and it'll give us this thumbs up or thumbs down. It'll tell us if this program is ever going to halt or not. That's the halting problem. And so at that point we gave up. We were like, this sounds really hard. And we didn't bother, and it's probably a good thing that we didn't, because this is the uncomputable thing. Turing now shows that there is no way to just look at the description of a program and know whether or not it has an inherent problem like an infinite loop in it. And so he's going to try to come up with a machine that can categorize descriptions of Turing machines as circle-free, meaning they do good work, or circular, meaning that they eventually get stuck in an infinite loop. And he does this by first assuming that it's possible to solve this problem, and then he shows an absurdity within that. So he asks us to envision some sort of machine H that can take as input the descriptions of other machines and can sort the output at basically saying, you know, is this thing circle-free or is this thing circular? So some kind of machine that can decide whether a machine is circle-free or circular without actually running it, right? Because you can't just feed a machine and ask it to run these things because you don't know, again, how long to wait before it's safe to give up. So you want some way of just by looking at the symbols that constitute the description of the machine, categorizing it as either circle-free or circular. So Turing says, okay, let's envision that we have such a machine that can do this thing. If we have such a machine such that we can do this thing, we can just start with numbers. We can just start with, say, the number 1 and on, and start feeding them into the machine. Now, one thing you could do is it is possible to know if a machine is well formed or not. So you could throw away any number that doesn't come down to some kind of formatted set of symbols that looks like this, right? If it doesn't look like a well-formed program, you throw it away. But you start feeding it numbers. And the very first machine that it comes across that is circle-free, we're going to call that machine 1. And we're going to take it and we're going to feed it into another machine. So any machine that's circle-free, we're going to take those and we're going to feed them into a universal Turing machine, and we're going to ask that your universal Turing machine to find a single digit from that machine's computable number according to where it's been found. So the very first circle-free machine that was found, we're going to ask the universal machine to compute its very first number and record its opposite. And then we're going to find the next, or this thing's going to find the next valid circle-free machine. We're going to feed it to the universal machine, and we're going to find its second number, and we're going to record its opposite. And what we've done is we've just created a machine that can calculate beta. But we just earlier proved that beta cannot be computed. So if beta can't be computed, but having a machine that can decide if something is circular free or circular leads us to being able to compute beta, then there's a problem, right? So it's logically impossible to have a machine that can sort programs according to circle free or not, because if we did have that, we'd be able to compute an uncomputable thing. That is the last step towards attacking the decision problem. Turing now spends the last few pages of the paper talking about first-order predicate logic. This is the part of the paper that I had to read over and over and over. I still don't think I fully got it, but what he does is he takes first-order predicate logic. So this is like philosophical logic. It's the ability to encode statements and give them true or false values and then attach predicates to them to say, you know, is something true or is something false? It's the language of philosophy. And Turing takes first-order predicate logic and he constructs formulas in it that are equivalent to Turing machines. So he implements in first-order predicate logic the universal Turing machine. And he shows that because he's able to implement, he shows there's an equivalence there. Because there is an equivalence between first-order predicate logic and computation, that embedded in first-order predicate logic is the halting problem. And so he does it in a roundabout way. Like after talking about the halting problem, he also says, okay, sure, we can't decide if something is circular, free, or circular. Let's see if we can do this other thing. Let's see if we can read the description of a Turing machine and find out if it ever prints a 0. And it turns out, no, you can't even do that. You can't even just look at a machine and say, will this thing eventually ever print out a 0? Turing takes his first-order predicate logic machine and using the same system builds a theorem. And he says, if this theorem is provable, if and only if this theorem is provable, then the machine that is part of the same system will print a 0. And by way of that, he says that if we had decidability, so if there was a decision, a way of deciding whether or not this theorem was provable, then we could determine whether or not any program would eventually print a 0, but he had already proven that there is no way to ever tell if a machine prints a 0. So he basically just found a version of the halting problem hiding inside of first-order predicate logic, and that was the end of the formalist camp of mathematics. And that was the end of Turing's paper. After showing his paper to his advisor, he actually then was told that someone else had come up with a very similar thing. There was a gentleman named, I think it's Alonzo Church, who came up with something called the lambda calculus, and Turing looked at it and said, yeah, okay, that's actually my machines, just written in another way. And he got a little worried, and he actually added a whole appendix to his paper that showed the equivalency of the lambda calculus to Turing machines. Alonzo Church's paper also showed that the decision problem was not solvable, and so this just sort of strengthened the cause. They sort of attacked it from two different ways, through this machine-like computation and through the lambda calculus, which is sort of like symbol manipulation again. And Turing ended up going to, I believe it was Princeton, and taking Alonzo Church as an advisor there and doing his PhD with him. So they sort of paired up from that moment on. The rest of Turing's story gets interesting and then eventually really depressing. I'm not going to go into the full details of it. He does end up working in Bletchley Park. He actually ends up building some real-world computers. A lot of people attribute the code cracking machine Colossus to Turing, but he actually didn't have anything to do with that project. But he did build some physical real-world machines, and he actually had a real large amount of influence and contact with von Neumann, who built sort of the von Neumann architecture with his team in the States. So Turing is sort of directly tied to the history of modern-day computers in that way. And I think that's where I will leave the talk for today. So thank you very much. I really enjoyed researching this paper. I tried to read it a number of times, and it wasn't until I gave myself this ultimatum of coming and talking in front of other people that I actually eventually got through it. If you want some extra reading material, the book that helped me out, these two books helped me out a lot. The Annotated Turing is absolutely amazing. Charles Petzolds, who also wrote the book Code, which is also an amazing book, took Turing's paper and annotated it. So if you leaf through this book, you'll see little gray squares with text in them. Those are Turing's original paper, and they're surrounded by page after page of annotations, just allowing you to understand Turing's paper. And so it took, like, you know, what's a fairly short paper and turned it into like a 350-page book. So that was pretty incredible. I don't think I could have got through the paper without it. Does anyone know this book, The New Turing Omnibus? It's so good. It was published probably late 80s, early 90s, but it's still super relevant today. 66 excursions in computer science, so there's all these small chapters on sort of the seminal problems and interesting ideas of computer science, and a whole bunch of them have to do with Turing machines and all sorts of other super interesting things. It's one of my most favorite books. Every once in a while, if I just want to read something cool, I pick it up, leaf through to a chapter, and read it. Another book that got me thinking about these ideas to begin with was Gödel, Escher, Bach, which goes more into Gödel's incompleteness theorem, where he was attacking the first two of Hilbert's sort of ideal formal mathematics system properties, the idea of consistency and completeness, and Gödel eventually shows that for any formal system that is powerful enough to contain arithmetic, you can't have both consistency and completeness at the same time. And so that I learned about that in Gödel-Escher-Bach, which is about much more. It's about sort of consciousness and the possibilities of artificial intelligence and sort of what our brains actually do. And then there's also a book that we were talking about before the talk, which was The Cryptonomicon, written by Neil Stephenson, and Turing is a character in that book, and that was sort of my first exposure to some of his ideas. So there you go. Thank you very much for listening to me today, and I'll put these slides up on Twitter. I'm at StungEye, and I'll probably post them sometime tomorrow. So thanks.
Cool. Thanks a lot.